one of the important concept is prime numbers, because all the most of the public key crypto systems are based on very large prime numbers. So we can start with the prime numbers. So as all of you know, prime numbers only have divisors of 1 and self. They cannot be written as a product of other numbers. Not 1 is prime, but is generally not of interest. Then 2, 3, 5, 7. Okay, prime numbers are central to number theory. The list of prime numbers less than 200 is 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, up to some numbers. And this is the some distribution of prime numbers under 2000 within each hundreds. So in first 100 we will have these ones, second 100 we will have another, and like that. This is all the prime numbers under 2000. Then next concept is factorization. To factor a number n, it is number n is to write it as the product of other numbers. Example, n is equal to a into b into c. Note that factoring a number is relatively hard compared to multiplying the factors together to generate the number, and this concept is used in cryptography. To factor a number is computationally hard, but to find the product it is computationally easy. The prime factorization of a number is number n is when it is written as the product of primes. 91 is equal to 7 into 13. 3600 is equal to 2 to the power 4 into 3 square into 5 square. Okay, so any number can be expressed in terms of prime factors. Okay. Next is prime factorization. Any integer a greater than 1 can be factored in a unique way as a is equal to p1. p1 means one prime number to some power, and p2 is another prime number to some other power a2, like that, pt into at, where p1, p2, pt are prime numbers and each ai is a positive integer. Okay, so any integer can be expressed like this. For example, 3600 is expressed as 2 to the power 4 3 square into 5 square, and 91 is expressed as 7 into 13. We have 91 is equal to 7 into 13, or we can say that this is 7 to the power 1 into 13 to the power 1. Similarly, 3600 is 2 to the power 4 into 3 square into 5 square. But we can express in another way, that is, we assume that capital P is the set of all prime numbers. Capital P is the set of all prime numbers. Then we can express any number in terms of all prime numbers, product of all prime numbers. That means this can be expressed as 2 to the power 0 into 2 to the power 0 into 5 to the power 0 into 7 to the power 1 into 13 to the power 1, 7 11 to the power 0 into 13 to the power 1 into next 17 to the power 0, like that. Okay. Similarly, this can be expressed as 2 to the power 4 into 3 square into 5 square into 7 to the power 0 into 11 to the power 0 into 13 to the power 0 into 17 to the power 0, etc. So this is actually we can express any, or we can express any number a. A is equal to pi or product small p member of capital P. Capital P is the set of all prime numbers. Small p to the power AP. AP, where each AP is greater than or equal to 0. Okay. So we can express any number like this. It is a product of all prime numbers with some power. That power may be 0 or more. നമുക്ക് അതിലില്ലാത്ത പവറുകളാണ് അതിൻ്റെ ഇപ്പോൾ ഏതെങ്കിലും പ്രൈം നമ്പർ അതിനകത്തില്ലെങ്കിൽ ജസ്റ്റ് എന്ത് ചെയ്യും ദാറ്റ് പവർ 0 കൊടുക്കും. ബാക്കിയുള്ളതൊക്കെ എന്ത് ഉള്ളതിന് മാത്രം നമ്മൾ പവർ കൊടുക്കും. ബാക്കിയെല്ലാം എന്ത് ചെയ്യും പവർ 0 കൊടുക്കും. സോ എനി നമ്പർ ക്യാൻ ബി എക്സ്പ്രസ്ഡ് like this. Any positive integer a can be expressed like this. A is equal to pi means it is product of all prime numbers with some power AP, where AP is greater than or equal to 0. Okay. So that is the concept. If P is the set of all prime numbers, then any positive integer a can be written as a is equal to like this. Then another concept is relatively prime numbers. Two numbers a and b are said to be relatively prime if have no common divisor apart from 1. Or we can mathematically that can be written as we will say GCD of suppose a and b, GCD of a b is equal to 1. We will call GCD of a comma b is equal to 1. GCD means greatest common divisor. അപ്പോൾ അതിൻ്റെ ഗ്രേറ്റസ്റ്റ് കോമൺ ഡിവൈസർ 1 ആയിരിക്കും എന്നുള്ളത് നമ്മൾ മാത്തമാറ്റിക്കലി ഇങ്ങനെ പറയാൻ പറ്റും. അങ്ങനെയാണെങ്കിൽ എന്ത് പറയും? വി വിൽ കോൾ ദീസ് എ ആൻഡ് ബി ആർ റിലേറ്റീവ്ലി പ്രൈം. ഓക്കെ. എക്സാമ്പിൾ 8 and 15 are relatively prime since the factors of 8 are 1, 2, 4, 5 and that of 15 are 1, 3, 5 and 15. Here only 1 is the common factor, so their GCD is equal to 1. So we can say that 8 and 15 are relatively prime. So that is the another concept, relatively prime numbers. Okay, we can ignore. Another concept is Fermat's theorem. This theorem we can use in to prove some other cryptographic algorithms. So and also for some performing some computations we can use the Fermat's theorem. So if p is a prime number, and a is a positive integer not divisible by p, then a to the power p minus 1 is congruent to 1 mod p. A to the power p minus 1 is congruent to 1 mod p. That is the Fermat's theorem. Then next is what is the use of this? So we can perform some computation easily by using this Fermat's theorem. For example, and this is also known as Fermat's little theorem. Another name for this one is Fermat's little theorem. And similarly, if we multiply on both sides with a, we will get another relation. This one, a to the power p is congruent to a mod p. Okay, so this is about the Fermat's theorem. So we can consider some example and then proof for Fermat's theorem. Okay, assume that our Fermat's theorem is a to the power p minus 1 is congruent to 1 mod p. A to the power p minus 1 is congruent to 1 mod p. This is Fermat's theorem. നമ്മൾ കണ്ടീഷൻ പറഞ്ഞിട്ടുള്ള എന്താണ്? that p does not divide a, or a is a positive integer not divisible by p. Okay. Then suppose we have some numbers like this. For example 300 283 എന്നുള്ളത് എന്താണ് 283. This is a prime number. നമ്മൾ നേരത്തെ ലിസ്റ്റിനകത്ത് കണ്ടിരുന്നതായിരുന്നു. This is a 283 is a prime number. Then if you want to compute some 300 to the power 282 mod 283, what will be the value? Then in this case we can write this as one thing is this is prime number, and 300 is not divisible by 283. Okay. Then we can use Fermat's theorem to solve this, because this is actually 300 to the power 283 minus 1 mod 283. So this is same as our this equation. Okay. So this part will become, so this will be same as 1 mod 283, that is same as 1. Okay. Similarly, if you have another relation, another one like this 50 to the power 461 mod 47. In this case, what will be the value? Here we know that 47 is prime number. 47 is a prime number, and we know that 50 to the power, similarly 50 and 47, if we are considering this 50 and 47, 50 is not divisible by 47, because 50 is not a multiple of 47. Then 50 to the power 46 mod 47 is equal to 1. ഇത് നമുക്കറിയാം, കാരണം എന്താണ്, by using Fermat's theorem. Fermat's theorem അനുസരിച്ച് 50 to the power 46 mod 47 is equal to, or it is congruent to 1 mod p, or it is 1. Okay. ഇത് നമുക്കറിയാം. അപ്പോൾ ഇത് യൂസ് ചെയ്തിട്ട് എന്ത് ചെയ്യാം, we can compute this one. This 50 to the power 461 mod 47 is same as 50 to the power 1 into 50 to the power 460 mod 47. Okay. So this can be written as, by our some property of congruences, a into b mod n is same as a mod n, b mod n, whole mod n. So this can be written as 50 to the power 1 means that is same as 50 mod 47 into 50 to the power 460 mod 47 mod 47. We can write like this, because a into b mod n is same as a mod n into b mod n. Okay. So this will be like this, and from this we can this will become 50 mod 47 will become 3 into, what will be the value for this one, 50 to the power 460 mod 47. So to compute that one, we can compute here. What is 50 to the power 460 mod 47. What will be the value? This is same as 50 to the power 46 all to the power 10 mod 47. Okay, but we know that this is same as 50 to the power 46 mod 47 into 50 to the power 46 mod 47 into etc. 50 to the power 46 mod 47 whole mod 47. That is A into B concept. 10 times we have to perform this one. But we know that this part is actually according to Fermat's theorem. This is A to the power P minus 1 mod P. So this will become 1 into etc. 1 mod 47. So this will become 1. So we can substitute that value here. This part will become 1. Then 3 into 1 mod 47, that is equal to 3, or 3 mod 47, or value is 3. So similarly we can perform some computations more easily with the help of the Fermat's theorem, and also we can use this Fermat's theorem for proving some cryptographic the correctness of some cryptographic algorithms. So before going to that, we have to consider the proof for Fermat's theorem itself, and only we can use the same thing for proving other algorithms. Okay.